Alright, so in this video we'll have a sample problem here that uses hydrostatic force, and doesn't look looks like a lot of other hydrostatic force problems, but the difference here is that we have not an open tank. So let's first, though, before we get into the details, let's look at the problem statement in the book. Here we have a supply line into a tank of water. It's not open to atmosphere. Instead, the supply has pressurized water from a pump upstream somewhere, and so that means the water entering this big reservoir is pressurized. Down here we have a discharge pipe that has a circular plate over it that's hinged about the central axis here, right? So here we're looking at the cross section that you would see if you were looking at the discharge pipe coming out here, right? So it's a circular pipe hinged about the central axis here, and is held shut by a latch. So a latch is being held here at the bottom, holding the circular plate in place, right? So just qualitatively here, we have pressure on the top of the hydrostatic, pressure acting on the top above the A-axis, and then we have larger hydrostatic pressure acting on the bottom. So you would imagine if that latch wasn't there, this would then swing open and the water would come out. So there must be a latch at the bottom to hold it into place, right? So holding the plate back from opening at the bottom. Okay, so the question here is, show that the force on the latch is independent of... Okay, so let's pretend that we don't know what the force on the latch is going to be related to. What are some important things about the system? Well, you might expect that maybe some of the geometry, so the height of the tank from the top down to the bottom, maybe the pressure of the supply, the water that's being supplied is important. And then another geometry, the radius, or the diameter of the discharge pipe, we'll talk about in the radius. So let's just say we'll express the force on the latch in terms of important parameters that we will be able to measure, or that are given in the problem statement, things that we could measure in a real system, like all the things that I just mentioned. But we'll see, a spoiler alert here, that maybe we'll see that this force is surprisingly independent of some of these seemingly important parameters, such as the pressure and the tank height. Okay. So again, my diagram here looks very similar to what we had in the book, but we labeled axis A here, the central axis, where we have a hinge or a rod here holding this, that the plate would rotate about if it were allowed to, but it's being held in place by a latch at B, and we want to know the force acting on the latch at B. Okay, so you could run through this being careful, but I think it's best to have a visual representation of what we're actually doing here. So we'll talk through some of just the equations here, but the pictures play an important role here. Okay, so what's unique about this is that we have our hydrostatic, the hydrostatic pressure profiles that we see often look like this, where we have a pressure prism starting at 0 if we're talking about a gauge pressure, which we typically do. So up at the free surface, there's no gauge pressure. The pressure within the fluid is the pressure of the atmosphere around it. And it grows linearly with depth due to hydrostatic pressure increases. So the further you go down, the higher the pressure, and it happens in a linear fashion. All right, but what's unique here is that this isn't open to the atmosphere. All right, so it's pressurized at the top of the tank. Well, that means that we're just taking a section of a typical pressure prism, or a pressure profile, and starting at some place that's non-zero. Okay, so what we really want to know, we'll need to relate the pressures down here on the near the discharge pipe to the important heights involved here. But here's what the pressure profile will look for our system. These are gauge pressures, meaning that even at the top, we don't go to a 0 on our pressure profile. Instead, we start at some non-zero pressure and increase linearly downward from there. So instead of this picture, we can think about this as a fictitious tank that has a higher, a larger height, that does go up to some fictitious free surface where the pressure goes to 0. Okay, and so I've tried to draw this proportionally, but the H then is just part of the tank. From here downward is our tank, but we add a section up top that represents the pressure head from the supply line pressurized water. So that's the head, the additional head we get from the pressure in the supply line. And so that would then, this height, if we write the pressure in terms of a height, is just P over gamma. And so then the total height we'll just call H naught for now. Okay, so in words, or written down here in everything I've just said and shown in the diagram, that the pressure profile we have in our actual tank is equivalent to an open tank that has a larger height, where H naught is P over gamma plus the H that is in our problem statement. And then we notice that that we can then use that as so we can basically go forward with this just being the tank of interest. We can just ignore that this is even the real tank, but we'll just have this going forward. And for this tank, our H sub C, our the vertical depth down to our centroid location, is this H naught. So this is the depth of the centroid for the circular gate. So let's go and do just draw a diagram with things, some of the quantities labeled appropriately here. So here's our gate, obviously not drawn proportionally, but here's our axis A of rotation and our latch location B. The height down to the centroid is also this Y location. So basically what I'm saying here is our geometry isn't inclined, otherwise we'd have to be careful what the difference between Y and H, for this system, because it's completely a vertical surface. They're exactly the same. So we have a relationship for that in terms of known quantities, or quantities that are given in the problem statement, quantities that we could measure in a real system. HC is just P over gamma plus H. That gives us the depth down to our centroid, and that also plays a role in our hydrostatic force. Our hydrostatic force is going to be the pressure at the centroid location multiplied by the area of interest. So for this, it's gamma HC pi r squared. So that's the magnitude of our hydrostatic force. However, we notice that it doesn't act at the centroid location. It acts beneath it because of our pressure profile. There's a higher pressure here at the bottom than at the top, and so our location of where the pressure acts is lower. And that occurs at this YR location, which we'll need to be a little bit more careful with over here. But before we do that, the other force acting of interest here is the force on the latch, and that's the unknown. That's why that's what the question is all about. What is the force on the latch? Okay, so once we have all that labeled, and we'll have to determine what YR is as we go along here, but we just sum the moments about the A axis, and that must equal 0 for the system to be in equilibrium and that the gate doesn't swing open. So the moment associated with the force on the latch is just going to be its moment arm, which is just the radius of that circular gate, r times the force, unknown force Fb, and then this is the unknown in the problem. And then that, if you do the right-hand rule, is positive about the a-axis, and then negative about the a-axis is the resultant force due to hydrostatics, due to our hydrostatic pressure. And there we have our Fr, which we know is gamma hc pi r squared, and its moment arm from the a-axis is yr minus yc. Okay, so what is yr? What is the location of our resultant force? That is given and derived in the book, probably derived in lecture, and given here in this formula. So we take the moment of inertia over the y location of the centroid times the area, so in the denominator there, and then just add that to the y location of the centroid. Well, we can just conveniently pull that over, and we have our yr minus yc, which is what we need over here, and that's just going to be the moment of inertia for a circle, which is pi r to the 4th over 4, divided by, well, yc is just hc, pi r squared is our area. Simplify here, we see the pi's cancel, 2 of the r's will cancel, we're left with r squared over 4hc. All right, so from that we can go back to our where we plugged in what the moments were and solved for the unknown, the force on the latch, FB. FB is then just equal to, let's see, this r squared over 4hc is that bit, the yr minus yc. We have the 1 over r from, that came from this r, and then we just have the resultant force due to the hydrostatic force, which is pi hc pi r squared. Do some simplifying noticing here. Importantly, you remember the spoiler alert earlier on that we expect pressure and any dependence on pressure and height of the tank to vanish. Well, that's all embedded. We have P over gamma plus H is what equals this HC. So when the two HCs cancel out, that's where that dependence drops away. All right, so we see there's a dependence on pressure and the height of the tank that will tell us what the hydrostatic force is on the gate. It also plays a role on where that the location of that force acts, but the combination of the two, that's where it drops out. All right, so the end result is pi over 4 gamma r cubed. And so here's our relationship, that the force on the latch goes as, well, the specific weight of water is that one fluid property we see here, but then r cubed. So the bigger, that's really all that matters here, is you need to make your latch strong enough going as r cubed. So if you have a bigger circular gate, a bigger pipe, you're going to need to withstand a larger force with your latch. If you make this smaller, you don't need as strong of a latch, right? So in the end, this is independent of pressure and